All right, so we're starting our new section, chapter 5, and chapters 5, 6, and 7 are where, in my opinion, I think the trig gets good. These are going to be the most meaningful sections that you're going to be using in calculus and in all your future classes. Before I get started, though, I wanted to show you a quick YouTube video that kind of helps sets the tone for this new chapter. And before I start it, I just want to give credit to the creator. I found his stuff on YouTube, Stuart Jekyll. So again, I don't want to be seen as stealing his material. I'll even give him a thumbs up. Yay! Anyway, we're going to watch this video and then we'll start this section.
What is a proof? A mathematical proof is a reason why a pattern exists, and developing mathematical proofs is a creative art. If you've been in school for a while, you might think of mathematics as calculation or computing, as in 1 plus 3 equals 4, plus 5 equals 9, plus 7 equals 16. But I'm bored already. You get the picture. If you add 9, you get 25, add 11, you get 36, and so on and so forth forever. I'm not sure why anyone would spend their time adding numbers together this way, especially when you can get a computer to do it about 1,000,000 times faster. If you're working as a computer today, you'll be replaced by a computer tomorrow, because computers never make mistakes and don't talk back. Mathematics is really about discovering patterns, about finding meaning in apparent chaos, about finding out why. So let's do some math. Do you notice anything odd about this pattern? 1 plus 3 equals 4, and so does 2 times 2. 1 plus 3 plus 5 equals 9, and so does 3 times 3. The pattern seems to continue. It's not obvious to me why adding together odd numbers should have the same result as multiplying consecutive numbers by themselves. What could odd numbers possibly have to do with perfect squares? Maybe it's just a coincidence. Where's my computer? A computer could confirm in a matter of seconds that the first 1,000,000 digits follow this pattern, but a computer could never tell you whether this pattern will continue forever, and it certainly can't tell you why. That's where you come in. Calculating is cheap and easy, but ultimately unsatisfying. But the conscious understanding of abstract mathematical truth, something that makes you uniquely and utterly human, that is priceless. Forget about calculating. Why does this pattern exist? The right answer is the answer that satisfies you. To find out why, don't just sit there. Try things out. Scramble the numbers and add them or subtract them in different ways. Use scissors and colors and pictures and anything else you can think of. The more ways you approach the problem, poke at it from all sides, the better you'll understand it. Over time, you'll develop an intuition for what's helpful and what's not. Mathematicians spend most of their time stuck, not knowing how to solve the problems they're working on, and most of the things they try don't work out. You'll spend your time as a mathematician stuck too, and most of the things you'll try won't work. You're on your own. Remember, you're a whole lot smarter than a computer. I hope creativity strikes. I'm Stuart Jekyll. Thanks for watching.
Alrighty, so hopefully that video set the tone. But yeah, what we're doing here is we're creating proofs. And the way proofs work is you're trying to basically tell me why something is right. Okay, so it's not really the final answer. I already know what the final answer should be, but I want you to prove it to me. I want you to show me all the steps, step by step, why it works. So just to get started, let me zoom in. An identity in trigonometry is a statement that two expressions are equal for all replacements of a variable for which the expression is defined. Okay? So that means that if you plug in 0, it's going to work. It doesn't matter what number you plug in. You can plug in 0, 1, pi over 2, negative pi, anything. Okay? And the two expressions are the same. So that's what you're doing. You just want to show that two things are equal. So here's what you're allowed to do in proofs. To prove or verify an identity, you must use basic algebraic manipulation adding, subtracting, multiplying, dividing, and trigonometric substitutions, because this is a trig class. Okay, to turn, and when you're dealing with a proof, you're going to have two sides. You're going to have the left side equals the right side. And what you're trying to do in the proof is you're trying to ask, are they the same? Okay, so what you're allowed to do that is you can transform the left side to the right side, or you can transform the right side to the left side. So you're allowed to make this look like this, okay? Or you can go the other way. Move this down a bit. It's up to you. And so you just have to choose one. All right? So for proofs, once you choose a side, okay, what I mean choose a side is you either pick the left side or the right side. You, first of all, don't mess with the other side, but I'll get to that later. And you can only, my cat's out of my notes, add and subtract the same thing on the same side. So what I mean by this is maybe you could do maybe plus 7 minus 7. Okay, you put them right next to each other and notice that's 0, so you're allowed to do that. Or you can multiply and divide the same thing on the same side. Or you can use identities to change expressions. And what I mean by that is what we did back in chapter 1, where you had your sine squared theta plus cosine squared theta. And that's already established because we already proved it. And so you can get that and you can turn it into 1. So if I had maybe this plus 7, we could say, oh, look, that's just a 1. Let me get rid of that arrow. And so you can say your answer is 8. All right? So you changed one expression and you turned it into another expression. You're allowed to do that. Okay? Add and subtract on the same side, multiply and divide on the same side. And again, usually we do the multiplying and dividing more. That's when you multiply something by 8 over 8, or in this case, usually, since we're doing trig, you may say is sine theta over sine theta. That's legal. You're multiplying by sine, but you're dividing by sine. And so it's a legal operation. All right, but now here's the big thing, what you're not allowed to do. And my cat is lying right on top of my paper. And I know, Gus, I know. So I'm going to try to yank it out from under him in one swift movement. Hope he doesn't freak out. Whoosh! He freaked out a bit. Okay. So you cannot use any algebraic manipulation that involves both sides of the equation. Okay? The reason why you can't do it is if you do things to both sides, you're assuming that they're equal. So doing so assumes that both sides are equal. And that's what actually we're trying to prove. We can't assume that. All right? So this means here are the things that are illegal. You cannot, and this is just for proofs. Not like forever or for everything. Illegal for proofs. So you can't add a number to both sides. You can't subtract a number to both sides. You can't multiply a number to both sides. You can't divide a number to both sides. You can't square both sides, you can't square root both sides, you can't raise both sides to a power, and you can't log both sides. Anything involving both sides, so both sides, 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 anything involving both sides is illegal. Okay? So imagine you have your puppy. Or let me just word it this way. All right? So every time you do one of this when you're doing a proof, somewhere in some part of the world, a puppy gets run over by a car. And it's your fault. Why? Because you committed the great sin of doing something to both sides during a proof. You can't do it. Can't do it. All right? Anyway. Don't kill me. All right. Anyway, I have a dark sense of humor. Before we start, though, I want to go over some basic stuff that happens a lot. Some algebraic manipulation that we see a lot when we're doing proofs. So the first one is the difference of squares. So whenever you have something squared minus another thing squared, you can actually factor this as a plus b, a minus b. Okay, it's a very popular form of factoring. So for instance, cosine squared minus sine squared, I can write this as parentheses cosine theta minus sine theta, cosine theta plus sine theta. Okay, for the next one, I can write 1 minus sine theta, 1 plus sine theta. I know 1 minus sine theta is cosine squared, but I'm just saying that you could split it up if you wanted to. Right? Cosine of the fourth minus sine of the fourth. This one's a little trickier, but notice that this is cosine squared theta squared minus sine squared theta squared. So the two inner parts are that. And so we can perform the substitution. I'm going to give myself some room. So we have cosine squared theta plus sine squared theta, cosine squared theta minus sine squared theta. Now I'm going to stop here because we're going to get to that stuff later. But notice cosine squared plus sine squared is 1. And so this would actually simplify further when we start doing the proofs. All right, so what I want you to do is work on the other three. I'll post the video to Canvas with all the solutions to that. But anyway, the other thing that you see a lot is multiplying by the conjugate. This is whenever you have an ugly denominator and you want to make the denominator look nice. A technique to do is to multiply by the conjugate. So for instance, if you have 1 over a minus b, notice the denominator is a little nasty. So we'd multiply by the conjugate. Okay. Now on the top, you end up with a plus b. And on the bottom, notice that this is exactly what we were doing up here, just in reverse. So this is going to be a squared minus b squared. Let me put it in black. I know it looks more complicated, but the idea here is that usually the a squared minus b squared will either be a trig identity, or it'll make square roots go away, or good things won't happen. And again, I can do the opposite. I can multiply this by a minus b, and in this case, the answer would be a minus b over a squared minus b squared. So just like before, I'm going to do the top three, and I'm going to show you how this works. So I have 1 over 1 plus square root of 3. Notice the denominator is nasty. When I multiply by the conjugate, though, I have 1 minus square root of 3. And remember that we have to FOIL, but we already know what's going to happen. This ends up being 1 minus square root of 3. And then 1 times 1 is 1. Minus square root of 3 plus square root of 3, they cancel. And you get minus square root of 3 squared, which is just 3. So that ends up becoming 1 minus square root of 3 over negative 2. It's bad manners to have a negative in the denominator. That's bad manners. So I can rewrite this as negative 1 minus square root of 3 over 2, negative 1 plus square root of 3. So this one required a lot of simplifying, but notice the idea here is the denominator was nasty. We had an ugly denominator, and we turned it into a nice denominator. That's what multiplying by the conjugate does. So let me make this smaller so I can move on to the next one. All right, this next one is cosine x over 1 minus sine x. So here I have cosine x, 1 minus sine x. And so if I multiply by the conjugate in the denominator, that's 1 plus sine x. All right. So what happens is we end up getting cosine. I'll keep them separated for now. But on the bottom, you end up with 1 minus sine squared x. Okay. Now again, I'm not working on proofs yet, so I'm going to leave that alone. But notice 1 minus sine squared can turn into cosine squared. And then from there, you can do some canceling, and things will happen. So we'll get there on the next page. Right? The last one is maybe we have, again, 1 plus sine squared. So if I multiply by the conjugate, it has to be the same thing on the top and bottom. The conjugate of the bottom is 1 minus sine, so it's the same thing. You can't do different conjugates, because then it's not the same thing over itself, which means it's not 1. But anyway, so we end up with 1 minus sine x, 1 minus sine x. There's actually 2 of them, so I can say 1 minus sine x squared over, and then again, I have 1 minus sine squared x. And again, 1 minus sine squared. We can eventually change these into cosine squareds. But anyway, do the bottom 3. And like I said, I'll post the video to Canvas. But we got to keep chugging. So general guidelines for proving identities. So here's kind of the idea. You have to try, or some tips. Try working on the more complicated side first. Okay? The reason being that if you work on the more complicated side, you'll have more to work with. The more you have to work with, the more you can cancel, the more you can manipulate. You're not really creating things out of nowhere. The other thing you can do is look for obvious trig substitutions. Okay, that could possibly help. So the really obvious ones, like your sine squared theta plus cosine squared theta, things like that, are, and I always end up forgetting it, 1 plus tangent equals r. Yeah. So look for obvious ones. It might not be like there, but notice that, oh, look, if I factor or do something really easy, then this trig function will pop up. So look for obvious trig functions and try to work toward it. All right? If you can't see anything, then try getting a common denominator. That might help. Or you can factor, or you can distribute, or you can even add or subtract, as long as to the same side. Remember that if you add or subtract, it has to be the same side. Like plus 8 minus 8. Right? So knowing what to do, though, it requires a bit of foresight into what will happen. You have to, your math knowledge, you have to kind of do the factoring in your head and know what the answer will be to know if that's the right step to take or not. Okay? And it's something that It takes experience and patience. Okay, you just have to practice it a lot, and eventually you see it so often that you already know what the result's going to be. You're just thinking 2 steps ahead as you're writing. So your brain is like working on the next step as you're writing down the current step. But anyway, as a last-ditch effort, okay, try turning everything into either sine theta or cosine theta. All right? Because if you turn everything into sines and cosines, you can see if things will cancel out. Also, keep an eye on the other side. Make sure you're working towards it. You want to be working towards the right thing. So let's say you have ugly nastiness over here. But you have a denominator of 5. And let's say your stuff's equal to 2/5. Well, if you look at the other side, you notice that you already have your denominator. So don't do anything that messes with the denominator. You're only going to be doing things that mess with the numerator. Okay? So be looking at what the answer is, and if you already have a piece of it, kind of mentally push it aside and just work on what needs to change. Okay? Finally, the last thing is proofs are meant to be read by someone else. In this class, it's going to be me. All right? So it's like you're writing a little essay, except the essay is in math. You have to show every step. Okay? Don't skip steps. Don't be like, well, it's obvious, so that's why. No, if something gets replaced, you have to show it being replaced. Okay? If things get added or subtracted, you have to show them getting added or subtracted. You have to be organized and clearly detail what you're doing. Now, sometimes the math itself will tell you, but maybe if it's a big leap or something, you can write a little note on the side and tell me this is what I did. All right, so we're going to get into it. Now, before we start, here's all the stuff we learned in chapter 1. I mean, I'm not going to have it write it out because we've already done it. Remember cosecant, secant, cotangent, just reciprocals of sine, cosine, and tangent. Tangent, sine over cosine, cotangent, cosine over sine. Here's the identities. Now in this section, we're going to deal mostly with the main one and these two. But the other two come up, can come up, but not in this section, not yet. All right, and then here's the tangent and cotangent. I always forget these, so I'm not going to really get mad at you if you forget them. All right, anyway, let's start. So what I'm going to do, I'm not going to do, notice there's a lot of proofs. Okay, we have 16 proofs to do. I'm not going to do all of them. What I'm going to do is I'm going to do the left side, and I want you to do the right side on your own. I want you to have practice. Remember, it's building experience. Like the cheesy thing when someone says like you can't be good at a sport in one day, it takes practice. And you have those motivational posters, practice makes perfect, practice makes perfect. But a lot of people don't mentally apply it to math. They just want to magically know what to do. But it takes practice. You have to get it wrong 1,000 times before, no, not really 1,000 times, but you get it wrong a lot before you kind of say, hey, I got that wrong before. I probably shouldn't do that. Anyway, let's start. We're going to start really happy, and then they're going to get a little nastier toward the end. So first we have sine theta cotangent theta equals cosine theta. Remember that this is what we're trying to prove. Okay? So your first task is you have to choose a side. Do you want to turn cosine into this? Or do you want to turn sine cotangent into cosine? You can only do one. And so usually we pick the more complicated side because I have more to work with. And so what I'm going to do is I'm going to choose that side. All right? Now, after I choose a side, I'm going to write it out. And I'm going to do things to it until I get cosine as an answer. All right? So the first thing I'm going to do is cotangent theta. I know cotangent theta is cosine over sine. That's an easy one-step move. And that's the move that, I know what you did. You don't have to explain it, but I have to see it. You start with cotangent, it becomes cosine over sine. And then you can say, all right, well, now I have sine cosine over sine theta, and these cancel out. And when they do, I'm left with cosine theta. Happy face. And so that's a proof. Notice that I didn't really write sentences explaining what I was doing. I just kind of put them in an order. My steps were clearly noted. There's my first step. There's my second step. There's my third step. Okay? Don't go writing all over the page and have one step here and then somewhere else in the corner another step. It has to read like a book. I have to look at it and be able to follow with my eyes really easily how you're getting from the beginning to the end. All right. So work on the one on the right. Let's go to the next one. Tangent theta, cosecant theta, cosine theta equals 1. So again, we're trying to prove it. So we want to choose a side. I'm going to choose tangent theta, cosecant theta, cosine theta. And so let me rewrite it out. And then I'm going to make my substitutions. I know what tangent theta is, and I know what cosecant theta is. So on the next line, I'm going to put tangent is sine theta over cosine theta. Cosecant is 1 over sine theta, and cosine theta is still there. Okay, now this is really over 1. Little addendums, things like that you can kind of add in. I'm just trying to show you that this cosine is in the numerator and not the denominator. So now the next line, top times top times top, bottom times bottom times bottom. And you can see things cancel out. The sines cancel, the cosines cancel, and when you cancel due to multiplication, you're left with 1 as an answer. There we go. One thing I want to mention is that on the homework, you're going to have to be doing this, meaning that these homeworks are going to be different than the past homeworks. You're going to have sections where you have to write it on paper, and you're going to have to upload it. And you can upload it to Canvas, or you can upload it to the website. I'm just actually still thinking of which one I prefer. I want to make myself not go crazy trying to juggle between the two. Anyway, so work on the one to the right. It's a little similar. Actually, it's different, but it's not too bad. So let's do the next one. Tangent x plus cosine x equals sine x secant x plus cotangent x. So this one isn't really obvious right off the bat. We're trying to prove that this works. So I'm going to choose a side. I'm going to choose this side because it's more complicated. You don't have to, but if you have the more complicated side, you have more to work with. So working this out, I'm going to first rewrite it. All right. Oh, and by the way, in our class, we're being tested on communication. It's like a Collin thing. And this is how we're showing that we're doing communication in our class, is that you're proving things. You're communicating to me that you can show one side of an equation equals another side of an equation. Anyway, so one thing I can do is I can distribute. Why not? So this becomes sine of x secant x plus sine of x cotangent x. Notice that they're getting a little bit longer, but then I have this secant and I have this cotangent. I can turn those into something. So I move down, and I know that this is sine x. Secant is 1 over cosine, plus sine x cotangent is cosine over sine. Okay? So all I did was I changed these to what they really are. I turned them to sines and cosines. Now remember that this is over 1. This is over 1. And we have two separate terms. These terms don't mingle because they have different denominators. So on the top, it's just sine x over cosine x. The next one, I have sine x. And I know they cancel, but again, I'm writing it like a story. You have to show me every single step. So I'm showing that they multiply first, and now I can show that they cancel. And I already know that this guy is going to turn into tangent. And the sines cancel, so I'm left with just cosine x. And notice that that's the other side of the equation. All right? So again, this just took 4 steps. Each step was readable. Notice that every time I did a new step, I went down, 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 showing, and I lined everything up. I put the secant over the 1 minus cosine because your eyes can follow straight down and they can see what it turns into. Cotangent, I just look straight down and I can see what it turns into. Anyway, work on the one on the right, but let's keep chugging. All right, now we're getting a little harder. These are medium problems, not easy. So, I have cosine to the 4th minus sine to the 4th over cosine squared equals 1 minus tangent squared. So in the spirit of things, I want to choose the more complicated side first. So we're trying to see, are these the same? So I choose the more complicated side. And this is going to be cosine to the 4th of t minus sine to the 4th of t over cosine squared of t. Now, one thing that should jump out on this problem is this part right here. We dealt with them on the previous page. That's the difference of squares. And I know, and here I could go down, but I'm dealing with fractions and, well, it's really up to you. There's really no right way or wrong way. But if you're going horizontally, then you have to put the equal sign in between because you're showing me that you're moving horizontally. If you go down, you don't have to put an equal sign. Or if, it's all a matter of, you know how when you become a more proficient writer, you have your style of writing? It's kind of the same way in math. People have the style of how they do math. So here I'm going to put an equal sign because I'm going horizontally. For some reason, that's how my brain wanted to do it. But this is cosine squared t minus sine squared t, cosine squared t plus sine squared t. And then this whole thing is divided by cosine squared t. Okay, notice that you do have to write the t every single time. Don't get lazy and just write cosine sine. You have to put the inside of each expression. But like I mentioned before, this happens. And notice that that's a trig identity. That's just 1. So because that's just 1, I can say that this is cosine squared t minus sine squared t over cosine squared t. Then I look at my answer. Notice that my answer is 2 terms. So this right now is just 1 term. So I'm probably going to have to split the cosine and divide each of them by cosine because that'll turn it into 2 terms. So equals, so if I get my cosine t, cosine squared t, and notice cosine squared over cosine squared is just 1. Sine squared over cosine squared is tangent squared t. Okay, so notice here I did it a little different. I'm guessing in hindsight I knew that this would be really long, so I pushed it to the side. But notice that I went to the right and then I went down. But you can clearly see my process as I'm going. I showed that cosine squared plus sine squared. If you want to, you can cross these out and show that it equals 1. Okay? That leaves us with just cosine squared minus sine squared. I split the cosine up, and I work it out, and everything lines up. Notice that the cosines all line up, the sine, the right side all lines up, there's a minus in the middle that lines up. That's what I mean by legible. It has to be easy to read. And keep in mind for these homeworks, I'm going to be doing a lot of grading, because not only do you have a take-home assignment that I'm going to issue for this section, but you also have these homeworks, and I have to grade pretty much every single one. So that's going to take a while. So be nice to me. Make everything nice and neat. But anyway, work on the one on the right side. It's similar. To help you out, I want you to notice that 1 is the same thing as 1 to the 4th. So that's the only hint you get for that problem. All right, moving on. Let me shrink this a bit. We're fine. All right, the next one is 1 plus cosine theta equals sine squared over 1 minus cosine theta. So what I'm going to do is I'm picking the more complicated side again. And I'm going to write it out and see what I get. So I have sine squared theta over 1 minus cosine theta. Again, like we talked about on that one page, notice we have this in the denominator. So I'm going to multiply by the conjugate. The conjugate of that is 1 plus cosine theta, 1 plus cosine theta. So I'm going to keep them separated for now. So I have sine squared theta, 1 plus cosine theta. And here, if I distribute these, remember that this is just going to be a squared minus b squared. We end up with 1 minus cosine squared theta. But like I mentioned, 1 minus cosine squared theta, and again, I have to write the entire numerator again. Sometimes it can be a bit tedious when you have to write something over and over again. But comes with the territory. So 1 minus cosine squared is just sine squared. Okay. And now notice that I have sine squared over sine squared. They cancel. And I'm left with just the numerator. 1 plus cosine theta. Notice my proofs are getting a little bit faster. I didn't write out an extra step because they were already over each other. Anyway, there you go. Okay, do the one on the right. Pretty similar. Now let's do number 11. Tangent x plus cotangent x equals secant cosecant. So for this one, they seem both equal in difficulty. So you pick a side, the left side or the right side. And really, it's up to you how you want to do it. Now, I'm going to choose the plus side. I'm going to do this one both ways, because notice they're both about of equivalent complexity on each side. But let's say we start with this side. I have tangent x plus cotangent x. I want to see what that equals. So when in doubt, turn everything into sines and cosines. Tangent is sine x over cosine x. Cotangent is cosine x over sine x. Okay. Now my goal is going to be to try to get one denominator. And I can do this in hindsight because I have a computer. Yay. He's cheating. But now I want to get one denominator. And so you can, if you learned it to cross multiply, you can. It's kind of a sin though in math. Or if you're teaching math, it's a sin to use that word because people tend to overuse it. If you ask them, why are you cross multiplying? They're like, I don't know. I saw two fractions next to each other, so that's what I did. And a lot of the times it's illegal, but I multiply it by the other denominator. Okay. Notice it's the same thing over itself. Anything over itself is 1. You can do that. I multiply by the other denominator. So the denominator was cosine, so I multiplied by sine. The denominator was sine, so I multiplied by cosine over cosine. So looking at the numerators now, I can see I have sine x times sine x. On the bottom, I have cosine x sine x. Here I have cosine squared. And I have sine x and cosine x. Now the two denominators are the same. So now you got that and that are the same. So you can bring them together. And then finally, we can see that we have our identity. Sine squared plus cosine squared, that's going to turn into a 1. So if you're trying to, I'll know if you put a 1 on the next step, I know what you did. But if you want to show me in this line, what you can do is you can kind of, if you wanted to, you could circle it, put a little line through it and say that, oh, that's just 1. But it'll be easier to see if I just highlight it. Highlighters are useful. So that's 1 over cosine x sine x. I look at my answer. I notice my answer is two separate terms. It's secant and cosecant. Secant is 1 over sine. Secant is 1 over cosine. Cosecant is 1 over sine. And notice that I pretty much have what I need. I just got to do a little more work. You can't go straight from here to the answer. You're skipping too much. So we can say 1 over cosine, 1 over sine. And now each term is there. I got this guy. I got that guy. So I know this 1 over cosine is secant x. 1 over sine is tangent, sorry. 1 over sine is cosecant. Ugh. And there you go. Done. So there's the little story of how we get from tangent, cotangent. We do steps and you get secant times cosecant. Okay? So I know I promised you that I do both sides. So let me do that real quick. I still want you to do number 12, but I'm pretending it's not there. Okay, so if I have secant, cosecant, so if you had chose the other way, remember I'm not doing 12th. That's for you to do on your own. So if you did secant x, cosecant x, and that's what you started with, perhaps the first thing you would do is you would turn them into sine and cosine. So you would say this is 1 over cosine x, 1 over sine x. And this is 1 over cosine x times sine x. And this is where kind of hindsight comes in, only because I did it one way already. Notice that I went from sine squared cosine squared to 1. And so we're going to do the identity backwards. When I have a 1, I know that that's just sine squared x plus cosine squared x. And then I can divide each one by cosine sine. So this way was actually a little harder because it requires the foresight to know that you're going to go from here to here. Okay. Usually we see the trig function and we turn it into 1. And the foresight to go from 1 to the more complicated trig function was the big leap. So here the sines cancel. Here the cosines cancel. And I'm left with sine x over cosine x plus cosine x over sine x, which is sine over cosine is tangent x, cosine over sine is cotangent x. There you go. So it's up to you how you want to do it. The right side ended up being more complicated. The left side just had a lot of simplifying, but it's easier to see a trig identity than it is to create the trig identity. All right, so let me shrink this so they'll fit on the right side. So when I'm showing my work on the YouTube video, it all makes sense. There's that one. All right. Erase that. Erase all that. Erase that. All right. So anyway, now we go to the last 4. These are the more complicated ones. Well, actually, the last one's the most complicated one, but I even gave myself room for it. So I have 1 plus sine t over cosine t equals cosine t over 1 minus sine t. So I already know that I'm going to choose this side, because notice it has that denominator, and I know that I can multiply by a conjugate there. There's really no wrong answer. I'm just going on a hunch. It turns out if the hunch was wrong, then start again, but start with the other side. So I'm going to have that equation. I'm going to multiply by 1 plus sine of t, 1 plus sine of t. Usually avoid from distributing right away, because distributing makes things more complicated. And the idea here is I want to rewrite the problem. I want things to cancel out. And things usually cancel out if they're factored. So even though I'm multiplying, I have cosine t parentheses 1 plus sine of t. Here I have 1 minus sine, 1 plus sine. That's 1 minus cosine squared t. Ran out of room. Writing too big, that's too small. All right. So I know that this is a trig identity. So I have cosine t, 1 plus sine of t, and I know that trig identity is cosine squared t. Okay. Now this cosine t is going to cancel out with that squared. I notice we get our answer. 1 plus sine of t over cosine of t. We got the other side. Yay! So try that one. 14 is a bit tricky. I want you to try that one on your own. There's a cool thing you do to it, but let's do this last one. So 16 is the most complicated one of all, but I want you to do it on your own. Build character. Let's look at number 15 though. All right. So I have two fractions equals 2 cosecant of alpha. Now usually when you have two fractions, you want to make one fraction. Not always, but notice that this is one term. So having one fraction kind of makes sense in the right way to go. Once it's one fraction, it's one term, and then we can start doing some math. So I'm going to choose, all right, let me write it out. I have sine alpha over 1 plus cosine alpha. I'm going to do some multiplying, so I want to leave some room. 1 plus cosine alpha over sine alpha. Okay. So what I'm going to do is I'm going to multiply it by the opposite denominator. The opposite denominator is sine alpha. So I'm going to multiply it by sine alpha. Sine alpha. The opposite denominator is 1 plus cosine alpha. Okay. Now what does that get us? We have a common denominator. So this will be sine squared alpha. Okay. Over, don't distribute, kind of leave it factored for now. And here, when I distribute this, notice that these two are the same. So we end up with 1 plus cosine alpha squared. Now, yes, you could cancel, but then you're just going back where you started. So we have these two terms. They now have the same denominator. Since this one is bigger, notice that I'm just going down. And I'm trying to keep those plus signs lined up. But anyway, so now it's one fraction. And I don't know, for some reason I like the sine alpha to come first. It's illegal to cancel those, don't think about it. So, what do we got? So what we can do is now I can just try to do some brute force algebra. Maybe if we expand this, it's going to work out. So if I expand that, I have sine squared alpha plus, now remember when you're expanding, you can do the box if you want. Oh, sorry, it's not a plus minus, it's a plus on both of them. So I have cosine alpha, cosine squared alpha. Notice that this expands to be 1. There's 2 cosine alphas. And then plus cosine squared alpha. Okay, and that So what I'm highlighting in green is what that expands to. All right, let me erase the little box here. Hopefully you'll know how to factor stuff out, but anyway. And let me move a little space. One of the problems when you're dealing with fractions going straight down like this is sometimes you put them too close to each other and they kind of all blend into one giant fraction and it's confusing on the eyes. Anyway, so all of that divided by sine alpha, 1 plus cosine alpha. Now, one thing you might notice is I have sine squared alpha and a cosine squared alpha. I can put those together. Since I'm running out of room, now I'm moving to the right. But I have to put the equal sign to show the reader that I'm moving to the right. And then plus 1 plus 2 cosine alpha. And then I have sine alpha, 1 plus cosine alpha. So now I have sine squared plus cosine squared. I know that that's 1. And yes, you have to rewrite everything. Now you may already see what's going to happen. Your intuition's like, things are going to cancel. But you can't just write the final answer and be like, well, it's obvious. You have to walk through all the steps. So this becomes 2 plus 2 cosine alpha. Notice that I just did the addition. And now I'm going to do the factoring. Now I didn't utilize my space as I should have. I apologize. But notice the 1 plus cosine alphas now cancel out. Okay? So here, and again, since Gilbert has things, so I'm going to cheat a bit. I didn't do my spacing right. He's a cheater. All right, and so I'm going to actually put this below. Okay, and now that they cancel, we're left with 2 over sine. But I know that that's 2 times 1 over sine. And finally, 1 over sine is cosecant. Dun, dun, dun. So yeah, a lot of steps. I thought I gave myself enough room, and I didn't. But notice that this one required a lot of work, a lot of steps. I know it gets really annoying to write the denominator every single time you're going through it, but you have to do it. You can only do one thing at a time. So I added, that's a step. I subtracted, that's a step. I distributed, in this case expanded the 1 plus cosine, that's a step. Okay, I saw sine squared plus cosine squared, I put them together, that's a step. I simplified it to 1, I didn't highlight that in yellow also. That's a step. 1 plus 1 is 2, that's a step. Okay, even though you can do steps in your head, you have to go and write down each one separately, and that's kind of you telling your story of how you're solving this problem. Okay, now the very end, how to disprove an identity. It turns out that this is pretty much the easiest thing ever, as you can tell by how much space I gave it on the page. Basically, you find That shouldn't be there. Find any value for the variable for which the identity is not true. All it needs is one counterexample. That's it. One counterexample and you are done. So here, they're saying prove that this is wrong. Prove that it's not an identity. And for here, I notice that this is cotangent. Cotangent is cosine. Usually you would plug in 0 and you'd get something that works. But I can't plug in 0 because sine theta is undefined. So I'm going to plug in the next easiest thing I can possibly do. I'm going to say let theta equal pi over 2, because why not? Right? It doesn't have to be pi over 2. You could have said pi over 4. You could have said pi over 6. It doesn't matter. But I just did pi over 2 because that's a nice happy one that I can pick. And if I plug it in, cotangent squared of pi over 2 plus cosine squared of pi over 2, cotangent squared of pi over 2, cosine squared of pi over 2. I know that pi over 2, this is cosine over sine. So at pi over 2, cosine is 1. Wait, I'll just write it like this. This is 0 over 1. Cosine is 0. Sine of pi over 2 is 1. And here, cosine of pi over 2 is 0. Cosine of pi over 2 is... Wait, did I screw up? Oh, yeah. So notice that it actually does work. Cosine of pi over 2, cotangent of pi over 2 is 0. Cosine squared of pi over 2 is 0. And so you may be, 0 plus 0 is 0 times 0. That works. But if that happens and they're telling you that you want to disprove it, I had my notes wrong and I had that it worked. I'm just going to pick a different number. So, okay, they want me to disprove it. Let's try pi over 4. Why not? I'm sorry. So 4, 4, 4, 4. Cosine squared of pi over 4. That's square root of 2 over 2 squared. Cosine's the easy one. Now cotangent is cotangent squared is just 1. Cotangent of pi over 4 is cosine over sine, but cosine and sine are the same thing at pi over 4. And so after we do the math here, we end up with 1 plus 2 over 4. 2 over 4 is 1/2, and that's 1/2. And notice you get a wrong answer. This would be 1.5, so 3/2, and that's not true. So even though it did work for pi over 2, it doesn't work for pi over 4. And all you need is one counterexample, and the whole thing is wrong. Okay, that's why it's so hard when in higher level math, a mathematician will publish a paper, and then people that read it say, "Hey, that's cool." And what they'll try to do is they'll try to find a counterexample to show that his theorem is wrong. And if they can't, then usually it takes a while for people to actually get a complicated proof and show that it's right in the real math community. Anyway, I'm just rambling now. But anyway, have a good one. And please let me know if you have any questions.